guys.
Today we're going to be talking about, everybody, today is going to be heavy on the theory, and it's some very important stuff that happens with in calculus. Today we're going to look at the fundamental theorem of calculus. Okay? Okay, there are two parts to it, and we're going to look at both parts today. The first part's relatively easy, the second part's the one that's more tricky. We're not going to be proving the fundamental theorem of calculus. We don't really need to know how to do that, okay? We just need to know what it is and how to use it, okay? And then also, too, know what some of the kind of consequences are, the corollaries that go along with it, okay? Which we looked at yesterday, things like average value and mean value theorem, okay? So, the fundamental theorem of calculus. We'll start off easy, part one. There are two parts to it. A lot of times you'll see in text, they'll call it the first fundamental theorem of calculus and the second fundamental theorem of calculus. I learned it as part one and part two, because I like the idea that there's one fundamental, it's a fundamental theorem, so it should be the theorem, and you shouldn't have two of them. So part one and part two is a little bit nicer in my book. Anyway, part one is the easy part, okay? What part one does is it basically tells you that integration, or that the definite integral is equal to the antiderivatives, okay, of the things. So it's fairly straightforward. Basically, the preamble to it is if f is continuous on the integral from a to b, and if big F is the antiderivative of f on a to b, then the integral from a to b of f of x dx is equal to big F of b minus big F of A. This should not be a surprise to anybody in this room at this point. All I've done here is just basically tell you what the definite integral is. Okay? And that's basically what the first fundamental theorem of calculus does, what part one does. Is it basically says, hey, the relationship here is that I'm basically linking antiderivative to the integral here. Okay? And that's what we're getting at. Okay? The actual proof of this is simple. It's actually not bad as a proof. It's in the book. You can look it up. This is section 4.4. If you just look up the proof in the book, it's rather quick and easy to pick up.
Will this
not too terrible. Huh?
Will this flip back whenever you like save it or something?
Yeah, it flips. It does it the correct way. I don't know why it mirrors it when flipping forward. It's weird, but no, the actual video plays forward. Okay, so but basically this is it. Any questions about this? I want to point out some things. One, notice here, we're defining the antiderivative. Okay, and if you remember from kind of the first week we started this stuff, we defined what an antiderivative means. Okay, basically means that f is the derivative of big F. So that means big F is the antiderivative of little f. So we're incorporating that in there. Also, too, notice we're using continuous as our word throughout here. Okay, we're defining this thing as being continuous. Okay, any problems with that? Okay, so yeah, this one's fairly easy because it's equal to something that we've seen before and we've done work with already. Okay, part one is easy. Kind of the consequences of part one. Okay. Basically, things that you get or kind of get from that. The first one is average value of a function. Okay, the average value of a function on an interval is going to be 1 over the difference in that interval times the integral, the definite integral, okay? That's our first thing there. So if I wanted to know what the average value of a function over an interval was, that will tell me what it is. How this might be used, suppose I wanted to know what the average velocity is of a particle or a car or something. I have an equation for velocity. I've got A and B. I can figure out the average by just dumping it in here and solving it, okay? This is fairly straightforward to do. You do need to know that this does in fact model average value. That does come up, okay? So do remember that it's 1 over B minus A.
So you take the antiderivative and then multiply it by the whatever constant you get.
Yep. So basically, we could do a very quick example here. Let's do the average value.
Is this the only consequence?
There's another one. That's why it's marked as 1 here. No, you're not. You just
What is he missing out?
Special.
adding a
It's
jit.
just Jim.
Okay. So let's say we're going to get the average value of f of x equals x squared plus 3 from 1 to 3. Okay. I wanted the average value of f of x. I do 1 over 3 minus 1 times the integral from 1 to 3 of x squared plus 3 dx. That's going to be equal to 1/2 times the antiderivative of this. So it would be x cubed over 3 plus 3x from 1 to 3. Okay? Which is equal to 1/2 3 cubed over 3 plus 3 times 3. Okay? Minus, you know what, I'm just going to make life easy for myself. Let's put brackets that I know where the nesting is. 1 cubed over 3 plus 3 times 1. Okay? And you would work out what that is, and that's the average value. Okay? Remember, numerical, once we've jammed in numbers, we're good. Okay, we don't have to go any further. If I wanted to go, well, let's go ahead and just go further for the heck of it. This is going to be 3 squared, so it's going to be 9 plus 9, so 18.
Can we just use our calculator for this?
What happens if you're on a portion of an exam you can't use your calculator? Ah.
Gotta
That
choose
happens.
somehow, Mr. Dowell.
Oh, okay, I gotcha. So this should be 14 and 1/2 of 14 and 2/3. So 7/3 or 7 and 1/3 is what this thing should be equal to. In actual terms, 22/3 should be my answer. Okay, when we work it all out. Okay, if someone wants to take that, pop it in the calculator and check me. Feel free to.
Why did
I
you put
trust
double
you.
parentheses around?
I was just trying to make sure we knew where everything was nested, and then I just got. One thing you want to make sure you do is that minus sign. You want to make sure it carries with the correct thing. Okay, and so that's why using parentheses is always good. Okay, but really it's just first thing evaluated. It's the antiderivative evaluated at 3 minus the antiderivative evaluated at 1. Okay, and you're going to have it. This should be your answer. Okay. All right. So that would be an example of average value. Okay. Oh, sorry.
Down a little bit.
Excuse me. Finish copying this down. All right. Really need to be moving. Okay. So the second kind of thing we get from this first fundamental theorem of calculus, first part of it, is the mean value theorem. for integrals. Okay? Basically what this is saying is that if there exists a c on the interval from a to b, okay, then, okay, the integral from a to b of f of x dx is equal to f of c times the difference between b minus a.
What does that say,
If there exists, yes, a c. Essentially what that's saying is, I drew a little picture of it up here for earlier classes. Basically saying is that if I have, well, I'll just reproduce the picture over here. What this is kind of saying here is, if I have the integral here from b minus a, if I were to kind of shade in that area there, that zone there is equal to a rectangle made from some random point c in between, where f of c, that's not the right location. Let's put c over here. That's better. Where f of c is the height of this rectangle, and the width is b minus a. Okay? Is what it's essentially saying there. That the area of that rectangle is equal to the shaded region from A to B. Okay? Is what it's saying. So there's some point in between. So, what it can mean is that there's a point in between A and B where I did a single rectangle, like I would do for a Riemann sum. Okay? It would be, the area of that rectangle would equal the integral. Okay? Is what the mean value theorem for integrals says. Okay? And you could find C. In fact, we did that yesterday in class. We saw an example of that. So I'm not going to. This is kind of graphically what's going on here. Okay, for those of you following along. Okay. Any questions about that?
Why is the C so close to the
Oh, I just drew it that way so I could. So because if I drew it closer to A, the way I drew the line. C could be anywhere in here, okay? And I wanted to make it look more realistic, okay, for the particular curve. But C could be anywhere, like in this picture here, C is a little closer to A, as you can see up here, okay? It all just depends on what your graph looks like, is where C would be. And remember, you'd be finding C analytically. You would not do it by graphing, okay? You would plug it in and do it. You would actually set up this thing and solve it, okay? And it wouldn't be too bad. You just calculate out this antiderivative, okay, and have it equal to, with the numbers in place, so you get a constant number. And that's going to be equal to f of c, okay, so the function with c in place of x times whatever that number comes out to be, okay? You're just solving for c, okay? It's not too terribly hard, okay? All right. We can look at examples. We'll see an example again of that on Monday, because there'll be some work involved with that. Okay?
Great.
Yeah.
Oh, I had on my notes yesterday. I don't know if this is just the way since we're going fast. But like I had part 1 and then part 2 and then these two things so we haven't gone over them.
Yeah, we're going to go over part 2 right now. Okay? Let's talk about part 2 now. Okay? So we saw the first part of fundamental theorem of calculus, and we saw sort of the things that kind of come from it. Right now what we're going to look at is the second part of fundamental theorem of calculus. So this will be part 2. So FTC part 2. Okay? Oops, go back. Okay. No, wait.
I think it's up.
There it goes.
So the average value of a function, the mean value theorem for integrals are parts of part 1?
Yeah, they come from part 1. Okay? They're not part of part 1, but using part 1, they go along with part 1, basically. Okay? The fundamental theorem of calculus part 2. This one is the one that's a little bit harder to see and harder to use. Okay? But basically what this one says is that if f is continuous on open interval I, then for all, or for every x, I should say, x within I, okay, the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. Okay? What this one is saying here is that it's more formally defining the relationship between the derivative and the integral. Okay? It's basically saying that if I take the derivative of the integral, I get the integrand back, the original function back. Okay? In a way, that's what it's essentially saying. Okay? And note the language up there reflects that. Instead of being on a closed interval, we're on an open interval, like we would be for derivatives. Okay? We don't define a zone from A to B this time, because instead we're saying I is any open interval where A is part of it, and for any value between in that open interval, this is the relationship between A
So
and
it
that
contains point A.
Uh-huh.
And for every.
Yeah.
So what does I represent?
I is an interval. It's an open interval. From where to where? We don't know. But it's from one point to the next point. Okay? Because it turns out for this, it doesn't actually matter what the points are you define, as long as it's a continuous open interval. Okay?
Basically, if you take the integral of the antiderivative, you'll get the
Derivative back.
derivative.
Okay. Or if you take, the
Or take the
derivative.
derivative of the
Integral.
then you'll get the original function.
Yeah. Okay. And we're going to look at some examples. Sorry, hold on.
You're good.
We're going to look at two examples of this because this one's kind of tricky to see in use. Okay. We'll look at an easy example first, and the easy example would be truly easy because it's just basically that, but with f of t replaced by an actual function. Okay. And then we'll take a look at a more difficult version, or one that's a lot harder to see what's going on. Okay.
I know this is separate from what we're talking about,
Uh-huh.
but if you just take the derivative of any antiderivative, then you'll get the original function,
You
correct?
should, yes. Okay. I say should because there could be situations where
Okay.
we can rig it so it doesn't necessarily work out that way. But yeah. Yes?
How come it's the derivative with respect to x, but it's f of t?
That's a good thing. Because note here, look at what I'm doing here though. This is saying I'm doing a definite interval, right? Okay? So if I were to work this thing out, okay, we actually work this thing out here. We're going to be doing the derivative with respect to x of from a to x of f of t dt. Okay, that's going to be equal to, it's not right now, okay, the derivative of this thing's antiderivative. So big F of t, or big F of x minus big F of a, right? Just defining that thing, okay? But then, what's f of a going to be? Is f of a here is not a variable, it's a what? It's a constant. So big F of a is a constant, it's a number. What's the derivative of a constant?
0.
0. So this really turns into the derivative, or this really turns into big F prime of x minus 0. And by definition, what's the derivative of big F of x?
F of x.
Little f of x. That's how we define an antiderivative, remember?
Yep.
Okay, and so that's sort of how this thing is working out, okay? If we actually were to write out our numbers, or write out what's going on up here, this is essentially, well, how we get to this point here, okay? Everyone got that?
Yeah.
The full proof of this, by the way, is a real pain in the butt, okay? The actual proof of this. But it can be done. Yeah,
What's the antiderivative of 0?
0.
Wait, so big F, can you tell me again what's the difference between big F and small f?
Okay, big F is the antiderivative of small f, okay? And so when we defined antiderivative, we said that you had a function big F of x such that the derivative of big F of x is equal to little f of x. That's what we meant by, and we call big F of x the antiderivative of little f of x, and that happens.
That is minus O?
0.
0.
Because remember, f of a is going to be a constant. The derivative of a constant is 0, okay?
So is that
Yeah,
No,
yes, you need to go ahead and take off, okay? All right, let's,
let's just do that.
is it your birthday, Jim?
No,
First on the right is here.
Okay.
And then the second.
no, actually.
Hey, birthday, Jim.
Happy birthday, Jim.
HB Jim.
Okay.
Thank you. I'm
HBD,
good on
Jim.
Mr. Dowell.
You
Party
too.
on, nothing, fun watching Star Wars.
It will be good. We'll have fun with it.
Sorry I have to miss it.
That's all right. Gotta miss it. Gotta do your thing. All right. Let's take a look at an example actually using. We'll look at 2 examples using real numbers here. Okay, like real functions. Okay. Sorry, I just threw a pin at you.
Oh, good.
You all right?
I think
It's
I'll
just like
recover.
it's like a 1 ounce
You
pin.
can't handle getting
Think
hit.
I'll
It happens.
So an easy example might be something like this here, okay? The easy one would be something like calculate the derivative with respect to x of the integral from 0 to x of the square root of t squared minus 2 dt, okay? Now, this one is easy. This one's easy because really, the answer here is just going to be this thing with x in place of t, right? Yeah, that's what it should be. That's what the theorem said, right? And indeed, that would be the answer, okay? This is kind of useful because we don't actually know how to do the integral of this thing right here, okay? We don't have a rule or a way to do that yet, okay? But because what the theorem says is it doesn't really matter what that is, okay? The answer would just be this thing with x in place of t. You can get your answer to the question rather quickly. And so we're good to go. That would be easy, okay? Makes sense, right? Not hard? No, hence why it's easy. Again, based off of the theorem. Now, anytime you just have an x up there like so, when it's just an x, this is how the thing's going to work out to be, okay? Which makes life nice, right? Now, notice though what I just said there. Just an x. Okay? Sometimes what?
It'll be x squared.
Sometimes it won't be just an x. And when that happens, things get a bit more difficult. Things get a bit more tricky. Let's take a look at an example of one of those, okay? So this will be harder, okay? Or hard. Okay? We're going to do the derivative with respect to x of the integral from pi over 2 to x cubed of the cosine of t dt. Okay? Now, this one's harder because I'm not dealing with just an x, am I? Okay. Instead, I'm going to basically, because it's an x cubed up there, it's going to change the way my answer comes out to be. Okay? I can think of this thing as almost now being like a chain rule. Okay? The book has one way of doing this, which is they say substitute another variable in for x cubed, then do x, y, and z, and blah, 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 and you get your answer out. We're gonna see that a little bit later on, exactly how that works. But we don't necessarily need to make it so difficult for us, okay? All we have to do is think about what cosine of t dt says, okay? We know that if I take, the idea is the derivative is supposed to just get rid of the integral symbol, right? Leaving us with the function appropriately evaluated. So if I did that, I'd be replacing t with x cubed, okay? But we also have this dt out there, okay, which should be replaced with the derivative of whatever x is, right? Well, x in this case is x cubed, so what's the derivative of x cubed?
2x and 1.
Derivative is
3x
squared.
3x squared.
3x squared is the derivative of x cubed. So, the answer to this thing should actually come out to be the cosine of x cubed times 3x squared, okay? Because that would be what this thing is basically telling you to do, okay? Cosine of x cubed times 3x squared. Now, if you're worried why, okay, if you're not sure exactly why that ended up being the case, another way I could solve something like this is to actually work out what this is telling me to work out, okay? I could do, go away, I could do the cosine, the antiderivative of the cosine of t, right? I could do that. What's the antiderivative of the cosine?
Sine.
The sine. Okay, not minus sign, the sine.
Plus
Okay.
C.
A lot of people made that mistake on the test, plus c. But this is definite, so we don't need to worry about that. Okay? So if I actually work this thing out here, pi over 2, this is a way I could check, basically. Pi over 2 of x cubed, okay, the cosine of t dt should be equal to the sine of x cubed minus the sine of pi over 2, correct? Because that would be the sine is the antiderivative of the cosine, and I'm evaluating from pi over 2 to x cubed. So that's what I would get there,
I
okay?
thought we got rid of the antiderivative though, right?
You're going to see what's going to happen here. Why I'm doing it this way, okay? So remember, we're going to take the derivative of it. So if I take the derivative of this, I'm also going to take the derivative of this over here, okay? Now, what's the derivative of the sine? So first and foremost, what can I do with sine of pi over 2? That's a what?
1.
One.
That's 1, right? So I can actually replace this with 1. Okay? And now I can do this derivative, right? The derivative of the sine of x cubed is going to be what? It's a what type of rule?
Chain.
It's a chain rule, right? So you do the derivative of the sine, keeping x cubed the same, and then multiply it by the derivative of x
So it
cubed.
would be cosine x cubed to 3x squared.
Cosine x cubed times 3x squared. And what's the derivative of minus 1?
0.
0.
I'm so confused.
So,
Look what we did there.
We wanted to do
is
that
it
right?
pi over 2
short
irrelevant
version.
basically to the...
Cool.
Yeah, actually it doesn't, those constants there, by what the theorem said,
Just,
don't really matter too much.
What about
Now-
the minus one?
Huh?
What about the minus one there from what?
Yeah,
Right
I know
there?
we got it, but shouldn't that be on the end of the?
No, it's the derivative of a
Taking
constant.
derivative.
I'm taking the derivative of this thing, the derivative of the constant is 0. So the minus 1 goes to 0. What I'm getting at here is I'm showing you kind of why I ended up, when I did it up here, I just wrote it as cosine of x cubed and then multiplied it by the derivative of x cubed. I didn't just leave it as cosine of x cubed, okay? Is basically is why I did this relationship, and I can show you why by actually doing out what this says to do, which is, and so you can always check if I can actually take the integral of this thing, okay? You can always use that to check to see if your answer came out correctly at the end, okay? The reason I didn't do it this method up here for the easy one is because, well, quite frankly, I can't really do the integral of that, okay? If you ask me what's the antiderivative of the square root of t squared minus 2, I would just be like, can't do that, okay? Or at least I can't do it easily, okay? And so, but I'm not doing anything crazy here, that's how I can get it back to this right here. By the way, if I made this like an x squared up here, or if I made this like x to the third, something like that, this would be x cubed squared minus 2 times the derivative of x cubed, which would be 3x squared. So I would do the same thing up there that I did down there. Okay?
Alright,
okay, can
so
you do it down real quick?
Wait, so after the t turns into x, and when you do
Basically, we're evaluating this thing,
yeah.
and so when the evaluation makes the t is the variable, and we're evaluating it from a to x.
Okay.
Okay.
can you explain
Explain that. Okay.
this to you? Once again?
Okay. So this easy one from our second part up here, we have the derivative of this right here is equal to f of x. So f of t is this inside part here. The only difference between f of t and f of x is that is using t's instead of x's.
Right.
So all this one right here is saying to do is replace the t with x, which is what it should do. So you should actually have a square root bracket around that. Okay, and then that's it. That's all it is.
2 volts, right?
Okay, did I not put it back up here? No, I did.
You did.
Uh,
And then, so how'd you get, like on this part one, I get how we plugged in the x cubed, but where did the 3x squared come from?
okay,
It's the derivative of,
it's because this thing is actually cosine of t dt. So when I'm doing that substitution, I'm putting x cubed in for the t, but then,
what does the d stand for in dt?
the derivative of t.
Oh, I thought that was the d over d of x.
Well, that stands for derivative with respect to x.
Oh.
And so in this case here, because I'm doing this, I'm switching t out with x
Yeah,
cubed,
yeah.
I have to switch out dt with whatever the derivative of x cubed was.
I got you.
That's how it came out to be
Not one that you
the other way around.
that one.
Yeah, it's kind of a trickier